for our second week. So yes, we will have first an introduction video about IFT and this Principia Institute by Eduardo Sato, and then we'll start with Professor Daniel Pershey from Florida State University. So yes.
Hello everyone. On behalf of Professor Gerson Francisco, who is the president of Institute Principia, I'd like to welcome you on our institute. I hope you have a great time here. We will show a short video about our activities here at Institute Principia. If you need any assistance during your time here, you can contact our team. We can be identified by the T-shirt and the name tag. So that's it. Can we play the institutional video, please?
Centro de produção e difusão do conhecimento científico e de conexão da ciência com a sociedade. Com atividades científicas desde 1951, tem atualmente 3 programas de atuação relacionados à pesquisa, educação e divulgação científica. No programa de pesquisa, acontecem eventos internacionais sobre temas atuais para diversas áreas da ciência. No programa de educação, a Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência, oferecendo uma tutoria científica com pesquisadores renomados. No programa de divulgação científica, existem diversas atividades com ênfase para o público jovem, como o Youth Science, o cinema científico e publicações em várias redes sociais. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
Okay, so after this video from the institutions that are making this school possible, there is a third institution that may be funding us, but they didn't deposit the money yet, so I won't say its name. If so I think just to remind you that this week we have 2 talks and then the coffee break. So before the coffee break, I'll make some announcements, but now, without further ado, you're ready to hear the first lecture of today. Thank you very much for coming, Daniel.
Yep. Thank you, Martin. So very happy to be here. So I'll be giving a lecture on neutrino detection. So yeah, could get the slides up. So yeah, I'll just say that I'm very happy to be here in Brazil. I'm from Florida up in the USA, which is as close as you can get to the latitude of Brazil and as you can in the USA, just flipped in the northern hemisphere. So, but I'm originally from Fermilab, just outside Fermilab, so I'm used to much more cold climates. So I'm very happy that you can have me here in the winter. So it's a nice reprieve from, the hot summers in Florida that I'm not quite used to. So yeah, very happy to be here to talk about, why I really love studying neutrinos and how we go about detect them and the diversity that we have in all these detection schemes. So I want to start off with a little bit of theory and just really the meat of why I study neutrinos. What are the really interesting things of why we want to study these? And the thing that I always tell students is, well, if you look at the history of developing the Standard Model, if you look at everything out in the Standard Model outside of neutrinos, from the discovery of the electron to the discovery of the Higgs, is something like 115 years. But if you look at neutrinos, they were first postulated in 1931, and we're still only about halfway to understanding them. So in that 90 years, we're still only halfway. So there's just a lot of very rich and interesting questions to ask related to neutrinos, and just a lot of experimental challenges to overcome. So yeah, the first thing is, do neutrinos interact with forces beyond the weak force? So we know that the cross sections are notoriously small, but they could these neutrinos could be participating in forces that are even stronger than the weak force. Particularly, the neutrino interactions with quarks and neutrino themselves are very poorly constrained. And there's been a lot of recent work in low-energy neutrino scattering to try to understand these non-standard interactions a little bit more and explore possible connections with dark matter. The next question too, so how will neutrinos help our understanding of neutrino astronomy? Now we can just flip the non-interacting nature of neutrinos on its head and basically say that neutrinos can escape from very dense media, so we can use them to study certain stars and astrophysical processes that we just could not with standard light detection. And so now neutrinos are becoming an incredibly important part of a multi-messenger astronomy portfolio. This was built up with initial discoveries coming from supernova 1987A and IceCube, in the past decade or so. And these two experiments are really shaping the future for looking towards a diverse precision era. And also, we need to know, why the neutrino and quark mixings are so different. We know from neutrino oscillations that the flavor and mass eigenstates are not the same. There's some mixing. But if you look at the mixing matrices between quarks on the left here and leptons on the right, neutrinos here, they're just completely different. The quarks follow some sort of hierarchical structure, which in a sense makes a lot of intuitive sense. But for the neutrinos, it looks like they just threw a bunch of marbles on the board and let it see where it lands. So this is, sort of odd thing that we don't understand. And it's one thing that by studying precision oscillation measurements, we can start to pick at which models are actually predicting this sort of behavior and see if we can actually understand something about this very high energy, this physics at a very high energy scale, which is producing this low energy behavior. And yeah, the fourth to last main question that I'll talk about is just, are neutrinos Dirac or Majorana? So this is the question, are neutrinos and antineutrinos fundamentally different particles, or are they just left and right-handed helicity states of the same particle? And this ties in pretty closely with how neutrino mass is actually generated. If you got a Dirac particle, then you basically just have some interaction with the Higgs, just with a really, really tiny Yukawa coupling. But if the neutrino is a Majorana particle, then you can have sort of a natural explanation to the smallness of the neutrino masses through the seesaw mechanism. So with that, this is what I'll talk about through the week. So today, really just give an introduction and talk about basic strategies for neutrino experiments. And then each one of the subsequent 4 lectures is really going to be trying to pick at each one of these 4 motivating questions that I had in the beginning. So yeah, tomorrow we'll look at neutrino interactions. Wednesday, go into neutrino astrophysics. And then lecture 4 and 5 will be covering oscillations and direct mass measurements. Right. So yeah, just right off the bat, a simple question that you could ask is how big will your detector be? So the cross sections for neutrinos are just small, so let's just do that calculation. If we think about a solar neutrino, maybe you want to hide all evidence of humanity and put some lead shielding around the sun so that you kill all the solar neutrino flux. How big would that shielding have to be? Well, the solar neutrino's flux goes up to about 15 MeV, so let's just take 7 MeV here as sort of a benchmark, and we see that if we're dealing with liquid argon, the cross-section is about 10 to the minus 42 centimeters. The liquid argon cross-section is this dashed blue right here. So we're really asking what the cross-section is right about there. And then we can go and think about the interaction length. That's going to be the number density of targets times the cross-section. You can really just work that out by dimensional analysis. 1 over centimeter cubed times a centimeter squared gives you 1 over a centimeter. So take the inverse of that, and that gives you a length. And if you just plug everything in, you get something like 400 light years. So these things are just incredibly non-interacting. It takes infinite amount, basically, of material to shield for them. So no matter what neutrinos we produce here on Earth, they are going to make it out into space. As much as we can do is, detect just a tiny fraction of them. And so what kind of detector mass would you need to detect that tiny fraction? So that's the calculation right here. Say that we want to have a detector that will record one solar neutrino a day. And this rate is going to be the number of targets, times the cross-section times the flux. The number of targets here I expended out as the target density, which we read up here, times the volume. Do some algebra of the volume. You can work out just in terms of these variables, plug in your numbers, and you see that you need a mass of something like 300 tons or so to detect an appreciable amount of neutrinos. So you really need to build things absolutely huge, sort of at the kiloton scale, to get a decent amount of statistics with neutrinos. And that's just always been the issue with neutrinos. We just need a lot of detector mass to learn anything about these guys. So yeah, the issue here is you just need to build huge detectors. So this is sort of the stereotypical huge detector that we'll talk about. This is Super Kamiokanda. Just you're looking at a 22.5 kiloton tank of water here with something like 11,000 PMTs just splattered across the surface. And looking for small little bits of Cherenkov radiation coming off from neutrinos interacting in this volume. And they only opened up the tank about once every decade, but I actually got to go down in 2018. I was working on some of the open tank work, specifically replacing the Tyvek reflective coating on the outer detector. But yeah, just being able to go down into this tank was absolutely mind-blowing. One of the best experiences that I had as a neutrino physicist. So yeah, you need huge detectors, but that's not going to do anything unless you have an intense source of neutrinos. So this is really looking at the gambit of what kind of neutrinos are produced by nature. So yeah, if you have very low energy, you have basically an analog of CMB photons that decoupled basically about a second after the Big Bang. And then once you get into neutrino energies here here's about an MeV to several MeV. MeV is sort of the natural energy scale for nuclear processes to happen. So whenever you have nuclear transitions, nuclear decays, you're going to get neutrinos that spit out. And we call those solar neutrinos coming from fusion in the sun. Terrestrial neutrinos, those are coming from beta decays within the Earth's core. And then we have reactor antineutrinos, neutrinos from a core collapse supernova. So those are really the nuclear processes that spit these out. And then we can also have neutrinos produced by accelerators, which is mostly produced by proton-proton collisions or similar, producing pions, which will then decay to a muon and a muon neutrino. The muon will also decay and give you a few neutrinos. So on Earth, we have accelerators. Like Fermilab and the LHC are producing many, many neutrinos in the sort of GeV to up to TeV scale. But of course, the universe can do even better. There are high energy protons that are bombarding Earth's upper atmosphere and giving us these atmospheric neutrinos. up to about a TeV scale. And then there are also neutrinos, both primary neutrinos and secondary neutrinos produced in cosmic accelerators, which go all the way up to about 10 to the 18 or 10 to the 20 electron volts. Yes? Yeah, the black line, it is, so that's the scale on the left here, that is the cross-section, right? So the cross-sections are very low energy, and then you see this resonance when you have W and Z production right up here at very high energies, right? So you need both the flux and the cross-section to understand event rate, so that's why I put them on the same plot. Yep. Yeah, okay, perfect. So yeah, we have all these scales of neutrino energies flying around, and we want to build detectors to study those neutrinos at all these scales. So we have right now we're working on pushing the energy frontier out on both directions. But right now we can sensibly detect neutrinos at the keV all the way up to PeV scales. And of course, these are very different events, so we have to use different detectors to detect them all. So just a couple, this one little detector here on the left is coherent cesium iodide detector. This is a small little scintillation detector with a single PMT, and it was looking at nuclear recoils induced by neutrinos, the sevens interaction, which you talked about last week. And then going on to neutrinoless double beta decay, that's a nuclear process, so that's going to give you, depending on which nucleus you're looking at, that'll give you a few MeV of visible energy that you see. And these are actually little bolometers, little microcalorimeters, so when a double beta decay interaction happens within these crystals, you'll see a small little temperature increase, which is observable. Then if you go up to sort of multi-MeV to GeV scale, you get the microboon experiment. This is a liquid argon TPC, so we'll talk about this later today and see very nice fine reconstruction that you can get in these detectors. And then going up another scale, we get to Super K, which is looking at oscillations in astrophysical neutrinos in water trunk of detectors, which you were already introduced to. And then at the very highest energy scales, you have these sort of cubic kilometer sized neutrino telescopes. So there you're just looking at IceCube, which is just at the South Pole. You drill really deep down, sink some lines with phototubes attached to them, and see neutrinos at the TeV up to multi-PeV scale. So what do neutrinos look like in these detectors? So of course, they're going to be very different depending on what technology you use. So at the lowest energy scales, you can't really track neutrinos so well, but you can certainly do things like calorimetry with them. So this is an example coherent waveform. So this is one interaction that was observed in that detector. There's no real background rate rejection in this detector. You can't do that so easily, so you can't really tell if this was a neutrino or just some other radioactive decay. But yeah, all that you see is a sequence of little spikes here, which are little individual photoelectrons interacting, being shot out in the detector and being collected in the PMT. Core A is similar, looking at these neutrinoless double beta decay. This is actually the 2 neutrino double beta decay spectrum along with random radiological backgrounds. And this is doing something similar. You don't have much, you really just see a calorimetric representation of your signal. But then when you get to these sorts of GeV scales or higher, you can actually do some interesting particle identification with all the information that you have here. So the microboon detector in particularly gives absolutely giant mass, sort of at the 100-ton scales, going up to 40 kilotons with the eventual Dune TPCs. You'll get resolution that is, that big, so something like half a centimeter or so. You'll be able to understand whether a charged particle was ionizing some energy in that particular region. So you get beautiful tracks, protons and electromagnetic showers that you can use to extract event kinematics to understand energies, which help you with oscillation analyses. This down here is Super Kamiokanda. So this is similar. Here you're looking at a ring of Cherenkov interaction of light. Which we'll talk about later. So here the main observable is now, instead of seeing tracks, you see a ring of light. And that ring is going to point in the same direction as the initial particle was, and the total calorimetric energy of all the hits that you see there is going to be a measure of the momentum of that particle. And then IceCube is also looking at Cherenkov radiation, but just at very, very high energies. So you don't really see a ring, you just see like a huge amount of fuzz distributed in different ways for different muons or electrons that are traveling through your detector. Yeah, so this is what it looks like, what the current state looks like, and we're of course trying to expand energy frontiers both on the low and high end, and we're doing that very successfully. Just in the last month we have new records on both the low end from xenon and ton. This is looking at 7s interactions from solar neutrinos. So this is a xenon dark matter experiment, so looking at sub-keV nuclear recoils produced in those 7s interactions. And all the way up to KM3 net, the ARCA distribution that they have, recorded sort of just by random chance. These very highest energy rare astrophysical neutrinos have a low probability of interacting each year, but they actually happened to see one that was on the tens of PeV neutrino scales. And then technology is actually really advancing to give us something like 10 to the 0 to 10 to the 21 EV detection, so just really huge massive scales. And I like to basically draw an analogy to biology. So the current state of the range of neutrino energies that we can study are similar to the mass range from these diatom plankton up to elephants. And of course, if you ask one biologist to study all these two organisms and everything in between, they wouldn't really know where to start. But if you actually look under the hood, everything comes down to DNA, which has these 4 different base pairs. And if you just take those 4 different base pairs and arrange them in different ways, you can get all this diverse and beautiful life that we see on Earth. And that is basically exactly what neutrino detectors do. It turns out we have also 4 different basic detection mechanisms. So if we, as experimental physicists, just arrange those in different ways, we can study everything from the size relatively plankton up to elephants. So yeah, what are those 4 basic mechanisms for neutrino detection? So yeah, scintillation, Cherenkov light, charge, and heat. So these top 2 are going to be small little bursts of light produced in your detector. And then you can also get ionized electrons, which will produce tiny little currents in your detector. Or, as in the case of Quarry, which I referenced to earlier, you can get tiny little burns of thermal heat introduced into your detector. If you produce an electron, say, through a beta decay, that's going to give you a couple MeV of energy, which goes eventually into bouncing around the thermal lattice and increasing the temperature. So yeah, where do all of these experiments lie on the space? So Coherent used scintillation. Cherenkov light, this was the IceCube and Super Kamiokande data that we looked at. The microbin experiment, what you're looking at is here. Here is the charge signal from neutrinos, but it turns out that argon is also a good scintillator, and so microbin sees both charge and scintillation. And then Quarry is the heat. And so yeah, these 5 detectors are what I'll be talking about today. So really going in depth of how they actually work and giving you an idea of all the specifics. But they are, I handpicked these so that you can get a good diversity of a good broad range idea of what possible detection schemes are out there. And just one quick slide there, which I already covered. Yeah, so let's just start going through each of these detection schemes and start off with scintillator detectors. When you have a passing energetic particle going through some material, that material is made up of atoms, so you can get that passing charged particle can boost some of the electrons up into an excited state, which can then decay back down. That is going to give you some photons, which we call scintillation. There's a lot of different, this all depends on the chemical structure, the atomic structure that the electrons have, so there's going to be a lot of different properties that the scintillation light can have. And so specifically here, this is looking at an organic scintillator, and you can see that you can have excitations both in a singlet or triplet state. You can actually get crossing over from a singlet to a triplet state, exchanging some angular momentum. And whether you do that, that will actually give you so-called fluorescence or phosphorescence, which happen at very different timescales. The lifetime for excited states in a triplet state is going to be much longer than in a singlet state. So these are sort of the physical parameters that might change in these different scenarios. And yeah, there are three main different types of scintillator. There are organic, which you see right here, and also inorganic and liquid noble, with just a lot of variety in the physical properties. The first detection of the neutrino, the Rines-Cohen experiment used an organic scintillator. So yeah, this is just a view of their detector that made the first discovery. And what you see is actually 5 different things in here. So these 3 big things are just big vats of liquid scintillator. And in between that, you have water doped with a cadmium salt. And so a neutrino comes in here, interacts with the water via an inverse beta decay like here. This is an experiment station at a reactor, so you have a high flux of antineutrinos, interacts on one of the free protons in water, makes a positron and a neutron. The positron will come to rest and basically annihilate with an electron in some atom and give you 2 back-to-back gammas, which will be measured in these scintillator vats, these 2 guys here. And the neutron will also bounce around until it finds a cadmium atom and capture on that cadmium nucleus and release some burst of gamma energy. And these are both going to give you photons, which will be measured in the scintillator vats. And the interesting thing is there will be some delta t, some time difference between these 2 signals. And so since you have those 2 correlated time signals, that will give you a lot of power for rejecting some of your backgrounds. So yeah, this is actually the second experiment that Rines and Cohen did. Does anyone know what the first one looked like? Okay, yeah, so the first one was just like a monolithic vat of scintillator. So what they no longer had these water planes with doped with cadmium. That means that they don't actually get neutron captures in the material that they had. Since they didn't have the neutron captures, they didn't get this second time signal here. They just got the first. And with just that first time signal, the backgrounds were just too high, and they couldn't really get any decent neutrino signal out. Their signal was swamped under the root and background statistics. Yeah, so going on to inorganic scintillators. So the basic scintillation mechanism here depends on, well, basically the band gap structure. So the cartoon on the bottom left here is basically what's going on. So a passing particle bumps one of the electrons in the valence band up to a conduction band, which you see sort of out here on the cartoon over here. And these excited electrons start traveling through the crystal. And they will continue traveling basically until they hit a defect in the lattice. So to make these crystals actually scintillate, you need to dope them with some additional activation center. And so that here your propagating electron comes to the activator site, to this doped atom, and it can sort of bounce off of this doped atom and become trapped in one of the upper electron orbitals of that doped atom. And what's important about this is now that electron will decay from its excited state back to the activator ground state and back down to the valence band of the crystal. But that gives you an energy which that is less than the initial energy of the conduction band. So this is really critical. This means that the crystal is basically going to be completely transparent to this photon, right? Because you're making a photon that is less energy than the band gap for the crystal. So it has no chance of actually getting eaten up and bumping up an electron from any of these other crystal atoms. So the crystal is going to be transparent. You're going to be able to read it out with some sort of light detector. So yeah, that's a basic mechanism. Why you really want scintillators. So scintillators just give you a huge amount of energy. So the black line here, so yeah, if you look at this plot, the x-axis is the band gap. So it takes that amount of energy to bump one of the electrons up into the conduction band. And then the yield here is the number of photons that you see per keV. So the product of these two is just going to be basically some energy, some number of photons that you get out per keV of energy that you put into the detector. This black line is exactly where 40% of the initial energy that you put into your detector gets transmitted into photons. So scintillators are just incredibly efficient at turning the initial energy of charged particles into photons. That you can work out something like tens of photons per keV in a typical detector, which means that you can push your thresholds really down low to about 10 keV keV scales or even lower. Yeah, so the plot on the right here, this is also really important. So you don't just have to make photons in your detector, you also have to detect them in some way. And you do that with maybe a photodetector with a PMT, which is going to have some quantum efficiency. This is a plot looking as a function of wavelength. The quantum efficiency for a specific PMT is this dashed blue. And then all the other, the green, black, and red distributions are the output scintillation spectrum for various types of scintillators. So not only do you need a scintillator that is going to give you a lot of photons, but you also need to have your photons be in the right wavelength range to be able to be picked up by a light detector. So sodium iodide doped with thallium here is sort of one of the most stereotypical, most commonly used detectors that we have. And I'll talk about coherent cesium iodide doped with sodium, which has a very, very similar emission spectrum, which is very much overlapping with the peak of this quantum efficiency for the PMTs. So yeah, moving on to an actual example of scintillator detector in action. This is a coherent cesium iodide detector. So this is measuring sevens at the spallation neutron source at Oak Ridge in Tennessee in the USA. And Coherent actually has multiple detectors studying both sevens on different nuclear targets and also looking at a few inelastic neutrino scattering processes. But we discovered here sevens with cesium iodide crystal inside this copper housing, just 14 kilogram detector. So at the time, that was held a record for the lightest neutrino detector that had done physics. And this detector is housed in some composite shielding system, which I'll talk about. But yeah, let's just talk about this housing for the main detector. So the crystal is down here in this copper housing. So the problem with some of these scintillators like cesium iodide is they are hygroscopic. If you just leave them out in ambient environment, water vapor from the atmosphere will make it into the crystal and degrade their light performance, make them unusable. So they have to be held light tight and airtight. So to do that, first you take the cesium iodide crystal, wrap it in some reflective Teflon, so any photons produced can bounce around and make it to your light detector. And then we'll put it inside this low activity copper shielding. And then we're going to shield this, we're going to just enclose this shielding with a PMT, put some sort of optical glue between the two so that you make everything very optically clean and light tight and airtight setting. And so this is going to be our detector housing. So, what are we going to do with the shielding? So yeah, this is an onion structure type shielding, which will be pretty common for neutrino physics. So yeah, the detector housing you see is right here. So we're just lowering it in. So the first step is to just put it on a base board, which is surrounded by both lead. These are lead bricks here, and high density polyethylene, the plastic here. So why would you want to use lead and polyethylene for shielding? Yeah, so the lead is very high Z, so it's very good at stopping photons. But basically, the bigger the nucleus is, the worse the nucleus is for shielding against neutrons. Sorry, the high Z is good for shielding against gammas, but the low Z is good for shielding against neutrons. You want something with a lot of hydrogen in it to shield against neutrons. So the neutron scattering off of a proton can lose basically, on average, half of its kinetic energy. But if you're scattering off of a huge nucleus like lead, the neutron is basically just going to bounce elastically off without losing much energy. So that's why we have these lead shielding bricks to kill out the gammas, and this plastic in here to moderate all the neutrons. And yeah, the next step here, we have this polyethylene built up around the detector assembly to moderate the neutron flux as much as possible. And then go ahead and build up these lead bricks more so that you can make the entire detector hermetically sealed and shielded from gammas. And this is a fully shielded detector, but we're not quite done yet. We still have a bunch of cosmic rays that are bouncing around through the corridor here, which can fake some signal in your detector. And so we want to know when a cosmic ray is coming around. So we have these plastic scintillator veto panels, an organic scintillator just completely surrounding, well, on 5 sides, all sides but the bottom, the detector, and then read out with a PMT on top of here. And then our last step, just for a little bit more neutron moderation, is to just surround this entire detector with these water bricks here. So when you have done that, put together those 5 pieces of the shielding, you have a detector that is ready to go and see your neutrinos. Yeah, so that is it for cesium iodide and the coherent experiment. So now moving on to microboon. So microboon is an argon detector. Yeah, sorry.
What energy of neutrinos can you find in the coherent experiment?
Yeah, so I'll talk about this tomorrow, go in depth for but it's basically looking at tens of MeV. So you're looking at pi and decay at rest fluxes. So a pi plus will decay to a muon and a muon neutrino at 30 MeV, and that muon will give you neutrinos up to 52.5 MeV, up to mu over 2. Yep, thanks. So back to liquid noble scintillators and the microboon experiment. So all of the liquid noble elements will give you some sort of scintillation with similar properties. But argon turns out to be, well, the cheapest and most widely used for neutrino physics, so I'll focus on that. There's a similar physical mechanism for producing scintillation based on argon. So usually it's a noble gas, noble liquid, so it's going to have no chemistry, be non-interacting. But when you have an ionizing particle coming through, you can either bounce an electron out of the argon atom and make it ionized. And it turns out that that ionized argon atom can find a neighboring argon atom and make an ionized molecule. That ionized molecule can recombine with an electron, but with an electron in an excited state. And the decay of this argon in an excited state will basically give you scintillation here. And you can also have, instead of ionizing the electron, going directly to an excited argon state, which similarly combines with a neighboring argon atom and decays. This photon that you get out here, that is very low wavelength. It is 128 nanometers, so that's in the very infrared, the very ultraviolet region of the spectrum. So that is something that we'll have to deal with. The light detectors are just usually much better at sensing optical photons in the sort of 350 to 700 nanometer wavelength regime. So somehow we'll have to shift that up to higher wavelengths. But yeah, first talk about, we can do a little bit of particle identification in these scintillators. So what you're looking at here is, as a function of time, the scintillation activity here is the black distribution. So all these little individual spikes, those are photons coming in. And then the blue here is just integrating up this black distribution, the black waveform. And you see that all in all, you get about 350 photoelectrons from this interaction. But you see that there are 2 very different time scales. This again comes back to the singlet and triplet excited electrons that are decaying. Those give you different time scales. So a singlet a photon will decay with a time scale of about 6 nanoseconds. A triplet electron will decay with a time scale of about 1500 nanoseconds. And if you look, this is exactly what a recoiling electron will look like. But if you look at a recoiling argon atom, an argon nucleus, it looks something a little bit more like this. So the nucleus gives you just a ton of light in the singlet state with a lifetime of 6 nanoseconds, and then just a small increase of activity with in the triplet state. So one thing that you can do is just look at, say, the ratio of the total light that is, singlet or triplet. And for the electron recoils like you see over here, the singlet to triplet ratio is something like 1 to 3, so much more triplet, long lifetime scintillation energy. But if you look at the recoiling argon nuclei, it's basically flipped. You get much more of the low lifetime singlet scintillation activity from those events. And the singlet to triplet ratio is something like 1 to 3 for electrons, flipped to 3 to 1 for argon recoils. So just by looking at the waveform, looking at the fraction that comes early in the waveform or late in the waveform, tells you something about the actual particle that was making the scintillation signal. Yeah, so I've referenced this a little bit ahead of where I wanted, but yeah, so scintillation from argon gives you a light at 128 nanometers. That is very bad for actual detection with photodetectors. So for instance, the blue curve that you see here, that is the quantum efficiency for a particular PMT. It doesn't start till about 300 nanometers, but the spectrum of light that the argon is giving you is down here at 128 nanometers. So you need some additional wavelength shifter to basically overcome this. So basically, you need some material that will eat up 128 nanometer photons and spit out photons in the hundreds of nanometers. And it turns out that there are a few ways to do this. Again, lots of chemical compounds can absorb light at different frequencies. But one pretty standard scheme that we have in neutrino physics is this TPB. This is the chemical structure here. And this 128 nanometer light is eaten up by these bonds in these phenyl rings. And then re-emitted in this green distribution. So yeah, the steps there, the argon emits over here down at 128 nanometers. The TPB is a very good absorber at these wavelengths, which is the green distribution up here. And then that TPB de-excites in this optical range, which is the green distribution down here, which overlaps with your PMT quantum efficiency quite well. So yeah, this is a critical step for being able to see scintillation light from any of these liquid noble scintillators. And so you'll see these in all the experiments. So microboon explicitly is right here. This is the photodetector system here. These are PMTs behind these sort of glazed plates here. And these plates have had a layer of TPB set right on top of them. And so light from all in the argon volume right around here will make it into this make it into this plate, convert from 128 nanometers to about 400, and be detected from the PMT back behind. So the coherent experiment here, this is looking at the argon detector in the coherent experiment, not the CZ-MIDA detector, does something a little bit it does something a little bit more clever, where you basically deposit TPB right on the light detector face on top of the PMT here. And that basically, it improves your efficiency for light collection. And since coherent is looking at 7's very low energy light signals, this is pretty key. And the cool blue haze that you see here is basically shining in an ultraviolet light that gets absorbed by the TPB and re-emitted in this blue spectrum of the TPB. So that's exactly looking at the emission of this chemical. And yeah, so microboon is more than scintillation. It is also a charge detector. It's a liquid argon time projection chamber. So for folks who haven't seen this, yeah, we just really love our argon because it is a liquid noble. It has absolutely no chemistry. So if you just ionize some electrons, they'll just hang out there. They won't get reabsorbed for order of several milliseconds after the fact. So you have a neutrino comes in here, says, say, make a muon and a proton here. That's going to give you some electrons. The trick now is put an electric field across this volume here, and the electrons will all drift in one direction to an anode plane. You can build an anode plane with a series of wires at different angles relative to each other. And these wires will all measure little currents as these electrons pass through them. Which of course can be read out. And yeah, the trick here is you are only basically instrumenting one dimension of your detector, which means that the number of charge of ionization charge detectors that you need basically scales like the cube root of the mass of the detector. So you can build absolutely giant detectors with this technology with a relatively small number of active channels and really keep your costs down. So if you want to make giant detectors with good energy resolution and tracking resolution, this time projection chamber idea is really the way to go. So this is exactly going back to our event display. This is what an electron neutrino candidate in the muon in the microboon detector looks like. And so yeah, it's really beautiful. You have all these different colors of along the screen gives you the amount of charge deposition as a function of yeah.
What is the amount of money it takes for you to build, for example, 1 meter cube of a detector with liquid argon versus maybe water or xenon? Because I've seen, well, many have water, some have argon, none have. I haven't seen any with xenon.
Yeah.
So what do we like I'm guessing it's the price difference, right? What the reason why you're not building it with other noble.
Yeah, so it basically does come down to price. So xenon, if you build it the size of Dune, would be like $10 billion of xenon. So you're not going to get that. Hydrogen and neon are even worse. They're even more expensive. So argon is just the cheapest, most economical, and so that really drives why we choose argon as the detector element. Yeah.
All right. Okay. Thank you.
Yep. So yeah, the red scales here, these are basically deep in the electromagnetic shower. You're going to get a lot of different particles building on top of each other here. The red down here, these are highly ionizing proton tracks. So you see there's just a lot of information coming from the charge deposition in these detectors that we can extract to learn about the neutrinos that are interacting in our detector. Yeah, so going into actually looking at microboon in depth a little. So you need liquid argon, so you need to hold this cryogenically, which is basically done with some liquid nitrogen system. So this cylindrical casing here is the cryostat, and that's going to be eventually filled with liquid argon. The box that you see here is the actual time projection chamber. You see it here in actual real life being introduced into the cryostat. And each there's going to be a bunch of flanges up on top. So these are actually going to be for the electronics for the signal wires. So these are going to read out the charge signals on that you're seeing. And then all these other utility ports are basically for argon filtration and removing non-argon chemical contaminants within the volume. If you look at this very fine, if you blow this up in a PDF, you'll see that there are actual vertical lines on this front face. What you're looking at there is a field cage, so that's basically going to be a giant voltage ladder. We're going to put a huge electric field. It works out to be about 500 volts per meter across this detector. So if you put a voltage divider around the outside, that's going to make sure that you have a constant electric field across the entire detector volume, which means that you won't have anomalies in the floating of, in the transport of electrons within the argon volume. And then everything is going to drift to this side, which has the anode plane here with several series of wires that are going to record the ionization in with different angles, so measured in the back with vertical wires, and then with two orientations above that, so that you can work out the full three-dimensional picture of what the neutrino event looks like. Behind this APA, you see here, these are the TPB disks, and behind that, the photodetector. So the light detection system is going to be there behind the anode. Yeah, so just the really brief ionization by charged particles. I hope we have seen this before, so maybe I'll go really quickly, but this is basically, there is a minimum ionization point where basically we have Relativistic particles like muons are going to give you something like about 2 MeV per centimeter in a material with a density of about 1 gram per cubic centimeter. But then if you get particles that are traveling more slowly, like protons, you'll get more ionization like up here. And then if you go to ultra high energy, ultra relativistic particles up over here, you start getting radiative losses, which is what will be happening for electrons. So yeah, particle identification in microboon. So you're looking at the charge deposit here. So you can really see that this muon is minimum ionizing. It has basically a light yellow or dark blue ionization signal on the color chart. And then each of these 4 protons come out from a breakup of an argon nucleus, which are all very heavily ionizing and give you red and yellow deposition. So you're getting a lot of ionization loss per centimeter in these 4 proton tracks. And then if you look at electron energy loss, so electrons are basically always ultra-relativistic. They have this beta gamma of about 10 to the 4, which was always in the radiative regime for the beta block curve. That turns into an energy of something like E equals m gamma of about 5 MeV. So most of the electrons that we deal with, at least in microboon and higher energy detectors, are going to give you electromagnetic showers instead of tracks for electrons. This is all, there's going to be a critical energy above which electrons will start to shower. That's going to depend on the particular material that you're looking at, which is the table that you have here. So in water, you have pretty light elements, so that critical energy is pretty high. It's about 80 MeV. But if you go to lead, it's only really a few MeV above which you are entirely dominated by electromagnetic shower production. And the really interesting thing to look at here is the bottom plot. So the shower length is relatively inelastic with the amount of energy in it. It goes with the logarithm of the energy of the shower over this critical energy, which means if you look in the plot, the difference between this green distribution and the red distribution is a factor of 1,000 energy, but only a factor of 2 in distance. So only going from about 20 up to 40 centimeters of depth. And then, yeah, just looking at a couple more event displays in microboon. So this is now looking at heavily ionizing proton and electromagnetic shower development. So you can really beautifully see little gaps here, which is where all the energy is contained in a photon. You see great little blips and Brem activity here. And then you can see basically the same thing over here, where instead of making a proton, instead of making an electron, you are making a gamma, which is going to have about a radiation length several centimeters before it converts into an E plus E minus pair. Yeah, so that's it for ionization. So moving on to Cherenkov light. Yeah.
The difference in, I mean, why is not a straight line? I mean, it's just a kind of error in the detection.
No,
because there is some space between, it's not a straight line, right? So why is that?
Yeah, so maybe we can go back to the bubble chamber here. Right, the electrons and positrons are pretty light, so they'll get bounced around a lot in the material, and so they'll start to point in different directions. Sometimes you'll Brem off a photon, which will be invisible, it has no charge, which will later convert into an E plus E minus, which basically is explaining, you know, all the little, you know, curved behaviors here. Here you're basically, it's multiple Coulomb scattering. You're scattering across all the atomic electrons in changing directions. And then all the little gaps here are, you know, regions where the energy is carried by a photon.
Okay. And why can you say that it's a gamma, not kind of a neutron? Because neutron is also neutral.
Yeah, well, neutrons are going to interact hadronically. Usually what happens when a neutron interacts is it'll kick out a proton, which then will be, well, it's this guy. So it would look like a very heavily ionizing local track here at the vertex. But what you see is actually a development of a shower. So you know it went to an E plus E minus there instead of a proton.
Okay,
yep.
Great. Thank you.
Yep, thanks. So Cherenkov light. So this is thinking about superchemiocanda and ice cube detectors. So here, instead of actually moving electrons around in atomic orbitals, what you're actually doing is basically the analog of a sonic boom. You get, if you're traveling faster than the speed of light in some material, you get this coherent buildup of the electric field in a ring around your particle track. which will be observed to particle physicists who detect quanta of light as different as observed photoelectrons in a plane of light detectors like you see here. So there's going to be a particle threshold. You have to be going faster than the speed of light in that medium, which translates to these numbers, something like 1 MeV for an electron in water, or over a GeV for a proton in water. But if you are going faster than the speed of light in the medium, then you get light production basically given by this formula here. So this is the number of photons per unit length, per unit of wavelength, which basically is goes like 1 over the wavelength squared and is proportional to this sine squared theta, which implicitly has some information about the speed and index of refraction of the material that you're scattering in. And if you just do the calculation, integrating over wavelengths that PMTs are typically sensitive to, you get something like 250 or so photons per centimeter, as opposed to probably, if you look in a scintillator detector, you'll have probably about 2 orders of magnitude higher than that. So yeah, I wrote that out. So the con here is that you get low light yield, something like hundreds of photons per MeV. That's this 200 photons per centimeter, and in water you lose about 2 MeV per centimeter, and that is compared to something like tens of photons per keV for scintillators. So scintillators just give you tons of light. Here in Cherenkov detectors you have less light, but you have this fantastic pro where you get directional information. You see a coherent cone of light which tells you basically where in your detector the interaction happened, tells you something about particle identification, and tells you something about the track length of the particle. Going to particle identification here really quickly. Muons show up as sharp rings. So this is really just the cartoon of Cherenkov light making this coherent ring of electric field around the particle. But if you look at an electron with the same momentum in the detector, it will be a little bit fuzzier. That's because electrons are light, so they will sort of bounce around in your detector through multiple Coulomb scattering. And so this ring that you see will sort of just dance around. And you'll get a bunch of, you'll get both a main ring and sort of a bit of fuzz around it. This bottom left display here, this is a through-going muon. So this is not going to give you a ring, but going to give you just cohesive region of light deposition. And then you can also have multiple rings produced here from a pi zero going to 2 gammas. So again, you don't have quite the exquisite resolution that microboon has, but you can still use the pattern of light deposits here to understand what particles and with what energy are tracking through your detector. Yeah, so the super chemiocanda experiment, this is the stereotypical example. This is deep underground, a mountain in Japan. It has both an inner detector here, 22.5 kilotons, with a total mass of 50 tons. There's an outer detector surrounding this inner detector. The inner detector has these 11,000 20-inch PMTs. The outer detector has smaller PMTs, about 2,000 of them. And this was recently upgraded to have gadolinium, to put gadolinium doped into the water, which means when you look at this inverse beta decay interaction, when an antineutrino interacts on a proton to give you a positron and neutron, you'll be able to detect the neutron capture on gadolinium. I'll talk about that on Wednesday. This is basically what an atmospheric neutrino will look like. This is high energy, lots of rings, lots of relativistic particles. And this is the event display for the inner detector, and this is the event display for the outer detector. So this is why you have 2 detectors. You use the outer detector as a veto to make sure that you don't have some particles sneaking in from outside to make interesting things going on in the inner detector. So to see a neutrino, you want lots of stuff going on here, but not a whole lot in the veto region. And just really quick, this program has been going on for longer than I've been alive. So this started with chemiocanda in about 1980, which was 4.5 tons of water fiducial volume, measured proton decay, saw the supernova neutrinos from 1987A. This was upgraded Super K in 1996, which is continuing to chug along now, 30 or some years later. And we will soon have hyperchemiocanda coming online at the end of this decade, which will be another order of magnitude improvement up to about 260 kilotons of water. Really quick, just talk about the ice cube experiment. This is going to be the same idea, but just at a much larger scale. This is going to be basically a cubic kilometer of instrumented detector. The actual light detectors are lowered down on these strings. You see a few modules here with light detectors attached. And right now we have about a square kilometer, about a kilometer deep of light detectors, which will be upgraded hopefully pretty soon with a Gen 2 upgrade, going to basically 8 times the fiducial mass. And these are a couple of just the very high energy PeV neutrinos. These neutrinos are so rare that they were able to just call them. These are neutrinos Bert and Ernie. Not really sure why those are the names, but that's what they chose, so we'll stick with it. And yeah, the light deposition here, you see that there's sort of a core central region, which is really related to the neutrino vertex, and then the length of how distributed that charge is tells you something about the length of showers. And yeah, so the last experiment that I have to wrap up with really quickly is the Quarry experiment. So this isn't looking at for ionization or light energy. This is just seeing small little increases in temperature in your crystals. So this uses tellurium dioxide, which has a very low specific heat, which means, you know, if you put a couple of MeV from a double beta decay interaction inside this crystal, you can raise the temperature a decent amount on a little germanium thermistor. Germanium is a semiconductor, so its resistance rises exponentially. So you can see the voltage going through this resistor, given a different current, is going to change noticeably. And if you you can separate this out from these signals out from shot noise. If you lower your temperature very low, down to about 10 millikelvin. But if you can't achieve that, you can get absolutely excellent energy resolution down to sub%. And so, yeah, this is a buildup of the Quarry detector. Each one of these little cubes is a little 750 gram tellurium dioxide crystal. These are put in 52 crystals per one of these towers, and then 19 towers to make the full detector. Inside a large cryostat that will run at 10 millikelvin, so this is multi-stage. There are 6 different stages here, going from room temperature all the way down to 10 millikelvin. And then this is exactly what you have to look at the final when you're doing your analysis. So this is looking at 2 neutrino double beta decay, which is the broad green distribution. You see a lot of radioactivity here introduced by your shielding and different parts of your detector, which you have to keep very close tabs on. You have to say everything that you put in the detector very, very carefully for these experiments. And it's also worth noting that you see individual peaks, which will be, say, gammas of a specific energy. And then you have, say, Compton shelf like behavior, which is distributed across the air. So yeah, this is that was the 2 neutrino double beta decay result that they have, and this is them looking for neutrinoless double beta decay. It is unfortunately quite close to. This is not neutrinoless double beta decay signal. That is a decay of 2, basically the pileup of 2 cobalt-60 nuclei decays, which is unfortunately close to the Q value. So this is another thing to watch out for. Make sure that you understand the radioactivity in your neutrinoless double beta decay signal very, very well. Yeah, so sorry I had to wrap up very quickly, but you know, neutrino physics is just connected with a lot of really open, really interesting open questions of the universe. But really answering those questions requires you to build detectors that span something like 20 orders of magnitude of size and energy resolution. Yeah, so I discussed the basic detection strategies today, so that, you know, later in the week we can talk about more of the applications to the physics. And yeah, that's it. Thanks.
Okay, so as you know, this week the schedule is very tight because we had to fit 3 lectures in the morning. We don't have all these full discussion sessions, but anyway, let's take 2 questions, and then after the second talk, we'll have a coffee break, and also you can get the speakers during coffee break and lunch. So 2 questions. And as last week, we can take questions in Portuguese and Spanish, of course.
So about scintillators, you said that they were they detected interactions only with electrons because they excite the electrons to the conduction band, right?
Right. Yeah. So they're detecting neutrino interactions, but those neutrino interactions are producing charged particles. Those charged particles are, zooming past atoms, which are going to excite the electrons. Right.
Okay.
So the fundamental interaction for the detection mechanism is between the charged particle the neutrino produces and the atom.
So it can also detect Sievens, for example. You can detect Sievens with scintillators?
Absolutely.
Okay.
Yeah.
Thank you.
Yep.
One more question, yes.
Hi. First, thank you for the talk. I have a question. When you showed like the different ranges of neutrino energies that can be found, my question is, considering that you have like up to like PeV neutrinos getting to Earth, how come the really high energy ones are only found by IceCube or in like experiments like that and don't completely dominate the spectrum for the lower energy ones? Because as per my understanding, the neutrinos, like, they wouldn't react with anything. Like if they are this high energy and nearly
Right.
massless, how come only IceCube can see them instead of dominating the spectrum for every single other experiment?
Yeah, so the answer is they're just super rare. Like in a PeV neutrino, this IceCube will only see about one interaction per year, right? So super K is just absolutely tiny compared to IceCube. So the coherent cesium-iodide detector is as small to super K as super K is to IceCube. So you just need absolutely gigantic sizes to get an appreciable rate. So I'm sure you may have once a century, you might have a PeV neutrino go through super K. It'll completely blitz the detector. We'll have no idea what to do with it. But yeah, you need to build IceCube to actually get those rare events. Yep.
Thank you.
All right, so let's thank again the speaker.